ahead.
A student is asking, and if you can repeat this, that would be great. If you can briefly explain one more time why we do not feed the output to the next input and why we use memory.
So we are not using, at this point, we are no longer using memory, right? We are using the hidden state. So you could feed the output back to the input. Let me go back to a very complex structure. You see this, you see the structure over here, right? This is the most generic structure, in which case the output is being fed directly to the output layer, to every hidden state, and to the input. This is the most generic structure, right? So what we are doing by actually having recurrence across the hidden states is adding a great deal more flexibility to the entire model, as opposed to having everything stored in this one unit. Did that answer your question?
Yes, it does.
Yeah. And so as it turns out, if you're storing stuff out here, having recurrence back from the output becomes kind of irrelevant. So we don't really do it because the information is already here in the hidden states. So now let's go back. It also affects our analysis for stability and such like, which we will see in the next class. Now let me begin with the second half or the second, or the third, fourth quarter of this lecture. Now, so far, we've assumed that the recurrence is strictly left to right from the start of time to the end of time. So we only model dependence of an input on the current and past inputs, but in many problems, the entire input sequence is available before you make your inference, like in machine translation or speech recognition. So you see the entire input before you classify or translate it. In this case, it makes sense not only to model the dependence of the output at any time on the past inputs, but also on the future. Because if the past predicts the future, then the past can also be deduced from the future. Meaning, so consider this example. If I say when Tom was young, he played baseball. Then when I see the word Tom, I can expect he in the future. But then suppose I got this backwards and I were going from the end of the sentence to the beginning. The sentence was when Tom was young, he played baseball. But I'm looking at the sentence backward. Then when I see the word he, I know that the name that was being referred to was a male name. It's more likely to be Tom than Nancy, right? So there is, just as there's a dependence going forward, there's a dependence going backward. This looking at the present tells you something about the future. Looking at the future tells you something about the present. And RNNs can be extended to capture these direct dependencies on both the past and the future by making them bidirectional. This was an idea that was originally proposed by Shuster and Paliwal in 1997. So now the network has two distinct recursions, one that goes strictly left to right and the other that goes strictly right to left, and their outputs are combined in the final computation. So here's one block of a bidirectional recurrent network. The block takes an input sequence, and which could be an input series itself, or it could be the output of some previous layers in the network. And the output of the block over here could either go to the next block in the network or to an output layer. Within the block, there are two distinct components: a forward net, which this is the forward net, which processes the input from the start to the end, from time 0 through time t, and a backward net which processes the input in reverse from t backwards to 0. Now, in order to have this kind of structure, now we have to define two different initial values. There's an initial value for the forward net that must be specified or learned, and an initial value for the backward net as well that must be specified or learned. And then finally, when both of these computations are performed, their outputs are combined. So here is the forward net. It recurrently processes the input left to right from t equals 0 to capital T, and it outputs a series of hidden state values. Now, the forward net, although I'm showing this using just one hidden layer, the forward net again can be arbitrarily complex. It can have many hidden layers. The backward net processes the data in reverse from the end to the beginning. Again, to be clear, this is not the backward pass of backprop. Rather, we are recurrently processing the input, but backwards in time. And so this produces a series of backward hidden states denoted here by HB of T. So part of the definition again of this backward net is this initial state, which is HB of infinity. Again, this backward network can have multiple layers, although I'm showing only one layer. And the important bit is that at the end of the backward recursion, it produces a sequence of hidden state values. The forward and the sequence of forward hidden states, which I have represented with a subscript F, and the backward hidden states, which I have represented with a subscript B, are finally combined to produce the output of the bidirectional block itself. Most commonly, the combination is simply done by concatenation, and you may or may not have an activation afterwards. So what I mean by concatenation is that we simply append the forward and backward hidden state vectors end to end to get a hidden state vector HT. The dimensionality of these hidden state vectors is going to be the sum of the dimensionality of the forward vector and the backward vector. So the complete bidirectional RNN is formed of many such blocks. We could either have simple blocks where within each block you just have both the forward and the backward network have just one hidden layer, or you can have, and you have several of these stacked up, or you can have just one complex block where within the block the forward and backward nets themselves have many hidden layers, or you could have any combination of these. In either case, it is sufficient to understand the forward inference and backward and backprop rules for a single block, and the full inference forward computation or backprop or backprop computation simply requires repeated application of the computations for a single block. Now, I actually have some pseudocode for this over here, but
Diksha, can I go ahead with the poll, or
go ahead.
Okay.
There's one final poll, guys. I hope you can see it. This is the poll for those who are watching it. Yeah, we can stop this. So clearly, thank you guys. Share the results. This is false because bidirectional recurrence is only possible when you already have the future. So only if you see the entire input and you make only in situations where you have the entire input to make predictions can you use bidirectional recurrence. A day trader doesn't see tomorrow's stocks, so he has to make his predictions based on today and the past. A day trader cannot use bidirectional recurrence. Anyway, so I'll to save time, I'm going to skip my pseudocode, but please do look at the pseudocode. It's pretty clean. But let's go back and look at backpropagation in bidirectional RNNs. As in the usual case, before you perform backprop, we will first perform the forward pass, computing both the forward and backward subnets within the block and the final output of the block. And then for the backprop, we're going to assume that there has been some divergence computation, there have been whatever other backward computations coming down, and that we actually have the derivatives of the divergence with respect to the outputs of the block, the entire sequence of derivatives of the divergence with respect to the outputs of the block. Now, because you're looking at this blockwise, if you're performing backprop, as you go back, you're always going to have these derivatives available. And then now, remember, h of t over here was formed by concatenating the forward and backward hidden states. So the dimensionality of h of t is the sum of the dimensionality of h of f and h of b. So the gradient for ht is going to have the same dimension as ht, which is to say the number of components for this gradient is going to be the sum of the number of components for the forward output and the backward output. So we can separate this gradient into two components. The forward component, so if I've formed the hidden state by concatenating the forward and backward hidden states like this, the gradient 2 is going to have a component for the forward state and a component for the backward state. So I can separate these two, and the forward component now goes down to the forward network, and the backward component of the gradient now goes down to the backward network. And now that we have gradients for both the forward and the backward nets, we can separately perform backprop on the two networks. So for the forward net, we are only going to consider the derivatives of the divergence with respect to the hidden state outputs of the forward network. And now we can, now we can just compute, perform backpropagation through time, start from here and work our way backwards and compute the derivatives for all of the hidden states going backwards, as well as the derivatives for all of these parameters going backwards, the derivative of the weights connecting these hidden states to the input, and the derivative for the input itself, the partial derivative for the input itself, obtained from the forward network. Again, remember the input could be the actual input or the output of the lower block in the network. For the backward network, now we're going to use the derivative of the divergence for the backward network that we had, and then we are going to perform backprop, but now the backprop is not going to start from the end and go backwards. Here the backprop, because the actual forward computation was done in this manner, now backprop has to start at time 0 and go forward to the final time, because backprop is always going to be against the flow of the computation performed during inference. So for the backward network, backprop will start from here and work its way out to this end. And as a result of this backprop, you're going to get the derivatives for each of these guys. You're going to get the derivatives for all of these weights. You're going to get the derivatives for these weights, which connect the input to the backward layer. And you're going to get a partial derivative for the input itself. Now remember, you got partial derivatives both from the forward network when you did backprop on it, and you got partial derivatives from the backward network when you did its own equivalent of backprop. And so to obtain the derivatives for the input, we are going to have to add up the partial derivatives for the input obtained from the forward network and from the backward network. And so finally, when you perform all of these computations, starting from the derivatives at the output of the network, you would have performed backprop and got derivatives here, backprop and got derivatives here. You would have obtained derivatives for these weights and these weights, for these weights, and finally the partial derivatives with respect to the input to the block obtained from the forward and backward networks would have been summed up to give you the derivatives with respect to the input to the block, and that can be passed on further down the network. So again, I have some pseudocode. I'm going to sort of skip the pseudocode and leave it to you for reference. So here is the story so far. Time series analysis must consider past inputs along with the current input. Recurrent networks look into the infinite past through a state space framework. These are through hidden states that recurs on themselves. Training recurrent networks requires defining a divergence between the actual and desired output sequences and backpropagating gradients over the entire chain of recursion, which is backpropagation through time, and, and followed by pooling of gradients with respect to individual parameters over time. Bidirectional networks analyze data both ways, from the beginning to the end and from the end to the beginning to make predictions. In these networks, backpropagation must follow the chain of recursion and gradient pooling separately in the forward and reverse nets. For the forward net, backpropagation must go from the end of time to the beginning. For the backward net, the backpropagation must go from the beginning of time to the end. But otherwise, all other rules remain the same. And so, in summary, getting to the end of today's lecture, RNNs are excellent models for analyzing series data, time series prediction, time series classification, and even for sequence generation. Now remember, we began the lecture by showing some excellent examples of sequences generated by an RNN. But nothing we've seen so far tells us how to use RNNs to generate sequences. We just showed the general form of computation that RNNs can perform for producing outputs at each time, but then this is more in the form of analysis. You give it a sequence of inputs, it produces an output or a sequence of outputs. How do we use it for generation? We'll talk about this in a later lecture. So in closing, RNNs are great models for analyzing series data, where the analysis itself requires you to consider data which have strict temporal structure, or sequential structure, like in time series prediction, time series classification, sequence generation. And as it turns out, recurrent networks can even simplify some problems that are difficult for multi-layer perceptrons and make them feasible. And we will see more of this in the next class. So that is the end of the class today. Thank you. Rashmi, can you stop the recording?
Yes.